So today I'm going to talk about something probably I don't know how many of you are familiar with this something called liquid wettability, but I can ensure that every day in your life you basically look for that particular stuff. Like any product that comes out, it doesn't really matter whether starting from toothbrush to the glass or pen, whatever the things, people look after this liquid wettability in a different perspective. Okay. Now, what I'm going to talk about here, I'm not going to talk about that particular essence that is already there, that's quite rich, but I'm going to talk about how to modulate different sort of other functional liquid wettability, which is mostly derived based on the inspiration from the nature. Okay, so there will be a lot of ample amount of introduction just for things go easy when we'll go through this particular presentation. Okay, so if you see, though it's look like a quite a massive information, but we'll go one by one. So this pink color is represented a droplet, not necessarily is a water or oil or whatever. It's a liquid. Okay, just keep it simple. It's a liquid. Now, when you put the liquid on a solid surface, we have regularly have seen, like just suppose we have a water droplet that we put in a glass or a granite top or the metal surface. What happened? Have you seen that sort of a detail? If you see, if you have not encountered that, my suggestion is that you just take a bit of a droplet, water droplet, and put it in a glass substrate. You will see initially it beat with some contact angle. I'll talk about what is the contact angle. Say like it's beat with a higher contour, okay, and then over the time its height get depleted, and then it comes to stationary. Now, why it does happen? Now, if I take a ethanol droplet, if I put on a glass substrate, it's immediately spread. That probably all of you have realized it, right? Now, it's all because of the balancing of the force. When you put a liquid on a solid surface, just imagine as this situation where it's planar smooth interface. You put the liquid. What happened? Three interfacial forces. This is indicated by red, black, and blue. There's three different forces acting on the droplet. And then if you have a 2D projection of this droplet anyway, it's 3D object, but if you have a 2D projection, you will get a unique 2 point on the right hand side and left hand side. And those 2 points are called 3-point contact. What are those 3 points or 3 phases? Those are liquid, solid, and gas. If you consider this particular droplet, the vapor state, some molecules still there, right? So that you can consider as a vapor state. And then this is basically pink color represents this liquid, and this is a solid, right? Now this black color represents the force that is called surface free energy. This is the equivalent term of a surface tension. Surface tension is basically for the liquid and vapor, okay, which is basically this red vector is presenting. Okay? This is the force, this is vector. Okay, it has a specific directions. Another one is basically interfacial tension, that between the liquid and the solid surfaces. But as they are vector quantities, they projected in a different direction, right? And what is the contact angle? If you take this particular tangential and this particular blue line, whatever the angle established, that is the contact angle. Okay. Now, when you put the water droplet on a glass substrate, initially it will be with a high contact angle, and layman language is a more height of the droplet given size, and over the time you will see that it's getting depleted, and then it will be stationary. After that, if you keep on monitoring, you will see that height is depleting, whether its contact line remain fixed. Why? Because most of the evaporation happen from the edges, and because of that you see the coffee ring effect, and that is the biggest problem when you look for the self assembly and all. Okay, I'll try to touch upon this particular concept at the end of my slide. Okay, now if you see this balancing of this force, that can give you a platform to predict quite efficient way what will be a contact angle for the given liquid on a solid surface. Okay, Young's basically introduced this formula. This is nothing but the force equilibrium. Okay, balancing of the force acting on this droplet, and if you have a 2D projection in the right hand side and the left hand side, two unique points. So basically, you have this red one is the surface tension, right? So this is a gamma LV and is a cosine component, right? Plus this gamma SL equals to gamma SV, right? It's just the balancing of the force. It's not a magic formula. Okay, that's the way Young introduced this particular equation, which is a smart, simple, and work pretty well if your interface is perfectly smooth. But in a real situation, things are different, right? That will have some sort of roughness, and that's the point you find contradictions or mismatch of your, theoretical predictions and your exact calculation of the contact angle. And you believe me or not, it took almost 100 years to realize that in this particular formula, Young didn't really accommodate that roughness factor, which has been corrected by Wengel. And that is the kind of situation that happened here. You have a rough interface and you're putting this liquid. What happened? The projected surface area and actual surface area is a different, right? So because of that, you see this anomaly, though it's not a such anomaly, it's just the roughness factor you need to include, and then it worked quite well. And these two situations, whatever Young model and Wengel model I just now explained, these represent homogeneous liquid wettability state. What that means? When you put the liquid on a solid surface, they establish a continuous contact between liquid and the solid. Okay, but there are some interfaces which doesn't follow neither Young's law or neither this Wengel wettability model or Wengel wettability model. Rather, it follows a completely different wettability principle, and that is called heterogeneous liquid wettability, which we found in a lotus leaf. Any one of you have seen the lotus leaf with the water droplet, or say like taro leaf? In Bengali, is say like pochu pata. Okay, even the cabbage leaf, rice leaf. There are many. Even the butterfly wings. Butterfly is a very light object, right? And if it's suppose in rainy days, if it is a weight by their wing, they cannot really fly, right? It will be disbalanced, right? And that's the reason nature gifted them with a super hydrophobicity. If you find any dead butterfly around, you can take their wing and you can put the water droplet. You will find a very hard time to put the water droplet on that wing. Okay. Now, what I mean by super hydrophobicity, it's basically ability of interface to extremely repel the liquid. More specifically here, it's water. That's the reason it's called super hydrophobicity. Now, when I say the extreme, it's a vague word, right? You have to give a quantitative estimations, right? So the contact angle has to be more than 150 degrees. Okay, then if you cross that barrier, then it's called super hydrophobicity. Okay, now if it is an oil, then it's called super oleophobicity. If this phenomenon happening underwater, then it's called underwater super oleophobicity or under oil super hydrophobicity. It's a very simple thing. If you just understand the genesis of this contact angle, liquid and all, it's very clear. Okay. Now, come back to the point that I said, like it's a fundamentally different approach. Why? It's a heterogeneous liquid. What I mean by heterogeneous, homogeneous we understood, right? Heterogeneous means when I say like the wettability of a liquid and solid, need not necessarily it's just the interaction between these two elements. There are some third component, external component, and that making a mess. It's a good way here. So it's basically for super hydrophobic interfaces like the lotus leaf or whatever the stuff. There, this entrapped air in a very rough interfaces, or say like the interface which has a very dual degree of roughness. I'll talk about that in little more detail. So there in the groups, there have a entrapped air which minimize the contact between the liquid and solid interface. And because of that, you see this heterogeneous liquid wettability and extreme repellence. Okay, this wettability cannot be explained based on the Young and Wengel. Okay, you cannot really find any roughness factor that basically explain this, because it cross this cosine limit. Okay, this roughness factor will be always more than 1, right? So it's not theoretically possible to explain the contact angle, high contact angle as high as above 150 with this Wengel, and forget about the Young angle. So it took almost 50 years from basically from here. It took almost 150 years to explain why lotus leaf repel extremely the water droplet. Okay, though it apparently look like it's very simple, but actual documented. This is the phenomenon we know day-to-day life, right? But if you see, this Young introduced, if I correctly remember, early 18th century. Okay, and from there it took almost 150 years to explain theoretically that what is heterogeneous liquidability and what is the genesis behind this, heterogeneous liquidity, or say superhydrophobicity, and that explained nicely by Cassie Baxter. Now these are all about kind of the range of hydrophilic, hydrophobic, and superhydrophobic. So I will touch upon this more or less that entire regime, right? If you now dip into a little bit this superhydrophobicity, then there's another term called adhesive and non-adhesive. Means when you have before I go further, this lotus leaf in South Asian country, it considered as a sacred leaf. Do you know why? Because you will find very difficulty to find a dirty lotus leaf. It's always remain, you will find always clean. If you look after other leaves, only in a rainy days it's a clean, but in other time it's a dirty, right? But in lotus leaf it's a remain very clean, right? That's the reason people have a belief that it's a sacred leaf, but that because of the superhydrophobicity. How? It has a self-cleaning ability. So whatever the dust particle that remain loosely fall on that interface, and once the water droplet is there, you put there, so all these dust and dirt particle accumulated, and once it tilted, it's roll off from this interface and leave behind a very clean, dry interface. Okay, so people really fascinated about the self-cleaning ability of the superhydrophobicity. Non-adhesive superhydrophobicity means, like, if you tilt slightly less than 10 degree, I'll talk about that a little more detail, 10 degree, then the beaded water droplet can easily, elegantly slide off or rolled off. Okay, and during that process is collect all these dirt and dust and leave behind a clean and dry interface. But you might want a control on adhesion of that water droplet for some other purpose, okay, but not in cost of compromised wettability. The interface continue to display superadhesivity, but you want that interface should allow to roll the droplet only in a higher tilting angle, so that you have more control on that interface for the rolling of the droplet, no loss transfer of the droplet from one place to another. Okay, that basically give more freedom in terms of open microfluidics. That is another segment. So how we can achieve it? So that is possible if you can establish this Casey-Wengel transitional state. Means you design the interface such a way that it give a kind of modest affinity, but not really pin there, right? So how you can do it? So people thought that topography could be a easy avenue. Okay, and in today's era, if you see based on this nanotechnology, you can come up with all sort of fancy uh, pattern interfaces in terms of this different sort of morphology. And when I say like two-tiered topography, it's a basically interface which has a microdomain, and the microdomains are further decorated with the nanodomain. For example, this particular one, you can see these kind of micro big domains, and they are with this nano fibril kind of stuff, right? So these coexistence are important. Even like this sort of stuff, this is reentrance topography is very specific if you want to design an interface which can repel both water and oil. See, if I keep on talking about this topic, it's a lot of things will come, but we have to restrict us in some point, right? So if you see like this particular topic started taking its shape from late 19th century. That's the point basically electron microscope getting available to many of the research lab. People can easily look at like what are the naturally existing interfaces this topography exists, and then people find a way to mimic them, and then you know all these living objects, the top surface always decorated with the wax and waxy type of molecule. So you naturally decorate the low surface free energy or waxy type of molecule, then you can achieve artificial superhydrophobicity. But there, in that those approaches, major I won't say like problem, but if you see the chemistry is a very blunt. It's just the hydrophobic modification, just the some sort of hydrocarbon chain that is what decorated on different sort of interface having fascinated micro nano domain. Okay. Rather than that, what we thought that can we play with this entrapped air, level of entrapped layer, not by modulating this topography, rather just by changing the chemistry. So can you have a platform where this liquid wettability and adhesion can be modulated just by playing with the chemistry? That is what the question we asked in IIT Guwahati when it started my laboratory in 2015, back 2015. And you can see, as I say, like the non-adhesive interfaces technical definition is the tilting angle has to be less than 10 degree, and for adhesive superadhesive interfaces, it has to be more than 10 degree, right? Another equivalent term is called contact angle hysteresis, and that doesn't really work for the sensile droplet. It's for the pendant droplet. What's the pendant droplet? Suppose you have a nozzle, right? It's kind of injection syringe. Through that nozzle, you can basically dispense the liquid, and you bring the interface just close to that, so the droplet doesn't really disconnect it through the needle. So you can advancing the droplet, just the contact. Once it's getting in contact, you measure the contact angle, and then they have a pump, so you can recede back the droplet. Okay, not pulling up, it's just the motorized, you sucking the water droplet, and the point is detached, you measure the contact angle, and this difference is called contact angle hysteresis. Okay, the difference between the advancing contact angle and receding contact angle. This difference of this advancing and receding contact angle means the contact angle hysteresis and this tilting angle, they give a similar sort of essence that what's going on. So if you have a more contact angle hysteresis, that means the interface is adhesive. If the more tilting angle, that means interface is adhesive. Okay. Now with that, we'll move forward and we'll learn how just by playing with the chemistry, you can derive a range of liquid wettabilities. I'll give you two essence in terms of like functional wettability while we are considering the heterogeneous liquid wettability as well as homogeneous liquid. Both the things I'll try to cover in this talk. And please stop me when I need to really just get stopped. Okay, just at least let me inform 5 minutes before. What time I have to stop? 15 minutes before. Okay, okay, sounds good. So so our approach is just to play with the wettability and adhesions, and then as this is a chemical approach, we can also associate different other component, right? Making this coating really mechanically stable, durable, not only mechanical property, other like electrical conductivity and so many things, okay, to be frank. Now, what is our approach is how we can play with this surface free energy, okay. There are three terms, right? The surface tension, surface free energy, and interfacial tension. So, in a way to play with the interfacial tension, you need to play with either surface tension or surface free energy. Now, surface tension is the inherent property of the liquid. So, if you are changing the property of the liquid, that means you are losing the integrity of the liquid. So, we should not touch upon that. Rather, we should play with the surface free energy, and that is the place is a problem. Surface free energy you cannot really change just by changing the topography. You have to play with the chemistry, right? And once you know that, then you can play with the interaction between liquid and solid. Okay, so the major parameter is surface free energy, and there have dispersion component, polar component, hard bonding, ironing, acid base so many and so forth, depending on what sort of functional group you are enriching at the interface, right? So that is very important, and how strategically you are doing it. So here we thought that this 1,4 conjugate addition reaction would be very handy. Why? This reaction happen in an ambient condition because the reactant what we choose has the acrylate and an amine. So Aja-Michael addition reaction happen at an ambient condition, and it doesn't really produce any side product. So, get rid of that side product, that concern is no more there in this particular system. And our approach is to design and derive some of these chemically reactive porous interfaces. Here we do very least attempt on playing with the topography, though we can do it. Here major emphasis is that how we can post modulate the chemistry, also like surface free energy, so that we can associate different liquid wettability. Now, you can see this is a porous coating on a glass, this is on a reactive superhydrophobic coating on a, so why reactive? They have a residual acrylate group, and this sort of modification ensure extreme water repellency. So you have an interface which extremely repel, but still remain chemically reactive, and you can play with that and can do some really interesting, derive some interesting interfaces, pattern interfaces. Also, you can derive a smooth reactive coating for slippery interfaces. I'll talk about that in more details. And chemically reactive graphene oxide. With the graphene oxide, you can decorate with reactive nanoparticles, and you can leave behind this reactive functional group and decorate them with the superhydrophobicity. Okay, so that is our strategy, and based on that strategy, we have derived a range of liquid wettability in our lab. Okay, so starting from in air different heterogeneous liquid wettability to submerged conditions different liquid wettability, all sort of things has been derived based on this simple strategy. Okay, not only that, recently our venture is in air bubble adhesion and wettability modulations, and that can be successfully applied on a gas evolving reactions or any kind of reactions which involve the reactant or product gases. So that is basically another very fascinating topic. If any one of you are interested, please visit those papers. Also, we recently introduced this sort of underwater super oleophobic coating which found a fish scale, and that can be used successfully to separate an oil and water from a mixture having the surface tension gradient starting from 35 to even 2.5. It is a wide range, right? And you can easily separate oil and water just based on gravitational force. No? So the environmental remediation is very much possible. Another topic is liquid marble. What is that? It's basically a soft material where the liquid can be encapsulated, and you can provide an isolated environment where the liquid is basically kind of encapsulated and protected with the hydrophobic or superhydrophobic particles. Now that is known for a long time. Okay, but what we are trying to do that how we can program the release of liquid, also like collisions of two liquid droplets. So you can program some chemical reactions and many other cool, interesting stuff. If you are interested, please visit some of this literature. As I said, like this superhydrophobic or superhydrophobicity can be combined with different sort of other interesting properties. Like one of the things is like electrical conductivity, and that can allow to design a sensor to recognize the voice. Okay, this is what we just recently communicated in advanced functional material, and with the like kind of machine learning tool, you can literally find another avenue for people who are know how to speak but they don't have the vocal cord. Like uh, during this oral cancer, the first thing doctor when they operate, depending on the stage of the cancer, when they operate, is just they remove this vocal cord. So disconnect this food pipe with the stomach so that there should not be spread of this cancer. So during that process, you like the patient lose the vocal cord, but they know how to move the muscles and give a shape of the voice to the word, right? So that is possible. So we use that Excel air and put on a air water interface. Whatever the water wave will produce, that will give the different height, and based on that, the submerged sensor will experience different pressure and contraction of the air, the entrapped air, contraction and expansion. That basically give the electric signal. It's a really fascinating stuff. Please go through it if you are interested. So this is not possible if you just thinking about just the topography. It's only possible when you strategically associate it with some sort of chemistry and select some of the useful components, right? So you can derive some nice features. Now, another interesting topic is a slippery interfaces. So when I started with this liquid wettability, I said like homogeneous liquid wettability, and people often think that homogeneous liquid wettability is not good. It's just the heterogeneous liquid wettability is good for many functional wettability, but that's not true. So it's almost like 2 decades since Jonah Eisenberg basically introduced this and I think this feature insert slippery interfaces, people started realizing that these smooth interfaces can also do a lot of miracles. And they some point could be better than this heterogeneous liquid wettability. Why? In case of heterogeneous liquid wettability, you have a hierarchy in topography. And if your interface is not properly decorated, then the light will get scattered by these rough interfaces, and often the interface will be very opaque. Okay, what I mean, like optically transparent such functional interfaces, you can find few examples, but it's quite rare. Okay, but when you have a principle to derive slippery interfaces, then you are rely on a smooth interface, but more capitalizing on surface free energy. Okay, that is the flavor I'll give you today. And once you match that particular these two parameters, then beaded droplet, instead of started rolling, it will slide off, leave behind no trace of that liquid. So it's doing a very similar job, right? It's doing very similar job, but here you can get a very optically transparent coating. Okay, but when this topic started with, there was some issues. I'll talk about that. But now you can derive a substrate independent, optically transparent, mechanically durable, thermally stable such sort of coatings. And I'll also talk about these pattern interfaces based on this principle, where the pattern is selective to a specific liquid, which is a rare concept. Okay, earlier people come up with a pattern interface, pattern wettability, where if it is a super hydrophobic hydrophilic, then also it's kind of super ambiophobic, super hydrophilic or oleophilic, that sort of thing. But here, situation are a bit different. I'll talk about that too in more details. Now, in my research group, basically, this is my first PhD student, Adil. So he started with these two commercially available reagent, BPI, branch polyethylenimine, and the 5-ACl, which has a 5 this cross-linking points. And in a particular reaction compositions, it undergo this 1,4 conjugate addition reaction, and it undergo solution to gel formations. Okay, through formation of this nanoparticle dispersion. This nanoparticle can keep growing in size, and they remain reactive in nature, which has been characterized with the standard FTAR spectra. And you can see here, this is the solution which is optically transparent. Over the time, it giving this milky solution because of this nanocomplex. And then if you allow more time, it will form this aerogel. Okay. This is in ethanol. So ethanol will evaporate out, it gives behind this heavable gel, and this gel is hydrophilic. So pink color is just given for the visual clarity. So you can see the beaded liquid can easily soak into this material, but once you post modify with the long tail alkylamine, then it becomes super hydrophobic. And it's not only just though it's an interfacial property, even if you incur some damage to this bunny shaped gel, the interior also continue to display super hydrophobicity. But our aim was something different. We wanted to explore this reactive nanocomplex which remain polydisperse, whether we can derive some sort of porous coating. And that's what Monideepa tried. And also other group members also tried to explore this nanocomplex to deposit following a different standard procedure like layer by layer deposition, deep coating, spray coating, and so many standard procedures, right? And depending on that, you can have a control on the porosity, thickness, and reactivities, and so on and so forth. So C started with the coating, which is highly porous, thick coating, and having two different functional group, reactive functional group. Now, once you do this octadecylamine treatment, where this primary amine of this alkylamines, more specifically octadecylamine with the residual acrylate, then you get non-adhesive superhydrophobicity. As you can see here, the contact angle is, static contact angle is 158, and if you beat the water droplet, then even at 7-degree tilting angle, it can easily slide off. And then fraction of contact area between solid and liquid, that is quite low, it's a 0.09, right? But if you take the same interface, go for another successive modification with this hydroxyl acrylate, where this amine can react with this acrylate, then you are installing this hydrophilic group and it become adhesive superhydrophobic. As you can see here, contact angles still remain above 150, so you can consider them as a superhydrophobic. But now, to roll the beaded water droplet, you need to tilt the interface almost twice degree, right? A 15-degree angle. And if you see the fraction of contact area, that is also got increased. Even if you measure the force of adhesion between the solid surface and liquid, that is almost twofold, depending on whether you have a monofunctionalization or dual functionalization. And you wonder, like, what's the big deal? First thing, this is done just based on the chemical modification. There's no topographical contribution, is not here. What I mean, we are not modulating the topography to achieve it, which is generally a routine practice in the literature. Okay. Second thing, you can derive a bulk coating. So even though you damage the top interface, the underneath interface also keep displaying this adhesive or non-adhesive superadhesive.
How does the force of adhesion?
So this is the force tensiometer. So you have a probe, kind of ring shape, a probe which can hold the liquid of your desired amount, and they have a programmed, and you can bring this droplet close to this surface, and so once it touch Then from there you can start detaching it, and there have a force balance, microbalance. It can exactly measure how much of force you need to apply to detach the droplet from their substrate. It's not a UTM. UTM force load will be very high, right? So this is a very is a micro balance to measure the force. There the principle is you measure layman ways similar, but there the force cell and all are very different. This is the force what I'm talking about, the micronewton. It's a very low. So it's a kind of a balance, micro balance. It's embedded with that system, and that's the way precisely you can measure this sort of force. Okay. Now, moving forward, as this is a chemical approach, we can do the same thing spatially selective manner. And once you submerge underwater, you can visualize the pattern. Okay. So just take a look at this video. So this is the pattern coating. You cannot really see anything with the naked eye when it plays in the air. Now, once you put this water droplet, can you see something there? It's a smiley face. Okay. And once you tilt this interface, the droplet completely gone. There's no adhesion, nothing. It's not a hydrophilic superhydrophilic interface, which is commonly people see, and where the water integrates selectively and remain wet. But this is a dry interface, right? So why you see that? It's because of its appearance underwater. So underwater non-adhesive interface look very shiny. You know why? Because of internal reflection. It's because of the internal reflection. Okay, so there have in this porous coating you have a trapped air, and when you submerge underwater, when the light fall, it's basically trapped, and then internal reflection takes place. The more you have a trapped air, you have a more this phenomenon, and you have a shiny interfaces. But when you have a some control on this sort of trapped air, suppose I can control to the lesser amount, then this internal reflection will be less, right? And because of that, it look less shiny. Okay, but if you take them out from this water phase, aqueous phase, they are dry interface. They maintain the superhydrophobicity. Okay, so this is the key aspect of this design. It's just a simple chemical modulation that give you so much of freedom, which cannot be realized just by changing the topography. Okay, that can do a lot of other things, but not this sort of stuff, right? Now, giving you this sort of flavor, I move forward to another topic, that is functional interface based on homogeneous liquid wettability. Okay. Now, this interface primarily inspired by the Nepenthes picture. I think most of you know this is a plant, but it's a carnivorous. It's a non-vegetarian. Okay, so it takes its nutrition from not from the soil. It takes from the insect. They don't have the hand to catch the insects, right? So nature gifted them with this property where this peristome can be lubricated, and once this insect sit on this peristome, it can slip into this pitcher, and this pitcher inside there have a digestive juice, sticky digestive juice. No way it can escape from there, and that's the way they satisfy their nutrients, right? Now, inspired from their Zona Eisenberg, she introduced this design. It's basically based on the hypothesis that if you start with a porous matrix, and if you choose a lubricant, liquid lubricant, and if you find a way to establish a chemical compatibility between the lubricant and the substrate, then this lubricated interface can slide the probe liquids. Okay, this is based on the assumption. This calculation only based on the assumption. So in her design, she took porous Teflon and then selected the lubricant, that is Krytox, the fluorinated molecule, chemically compatible, and if you put the water or oil, it can easily slide off. Okay, but the problem is it's a wet interface, right? And as it's a wet liquid, so over the time it can leach out. That is the problem. But this do a lot of other fascinating, cool stuff. So since that design introduced in the literature, people try out many things to come up with the porous structure and complete hydrophobization and then lubrication to get the slippery interfaces. Okay, but as I said, leaching of lubricant and durability remain a concern. Okay, I'm not going in depth. I think Robin Rass is also probably going to cover some of the things. He also does a lot of cool stuff. But our strategy was a bit different. So people, what they do to address this leaching of lubricant, they can form a SAM. Okay, so self-assemble monolayer, or even some point like quasi type of coating, which is not neither liquid neither solid. Okay, so that's sort of a coating, but our approach is fundamentally very different. What we thought that, can you derive a coating which would be completely non-fluorinated but capable of sliding both over water and oil? Not only just the water, even the oil. Okay, they will remain heat level and they will be absolutely dry in a room temperature, so that there will be no leaching problem, right? So it's a ambiophobic slippery interface. How we do that? So it's the same porous polymeric coating what I have discussed in the last few slides, and we have taken this comb-like polymer. So if you take this octadecyl polyoctadecyl acrylate, that octadecyl group that undergoes hexagonal packing. Okay, it's a crystalline polymer and it undergoes phase transition. It goes from a solid state in a room temperature, but if you go for the moderately high temperature like 51 or 52, it goes in a molten state. So undergo phase transition. So taking advantage of these key properties of this polymer, we lubricated this polymer in this porous polymeric coating, and then if you put the water or oil, both of these can easily slide off, as you can see here. I'll show you some of the movie as well. But if you take some control, suppose I have a lower analog of the same polymer which doesn't undergo this sort of crystalline packing. In that case, neither you see the slippery property against oil, rather it's spill all over the places as like a bare glass, and the water, even you tilt at 90 degrees, remain firmly adhered, it doesn't slide off. Now you say like, okay, what about the wax? Wax is small molecules, right? Kind of oligomer kind of things, and they also polymer. So if you take that, what happened? So yes, they slide relatively little higher tilting angle. They slide only water, but when it's come for the organic solvent can dissolve this wax, right? So crystallinity is compromised, right? So you don't get that property. But the polymer, once you prepare this polymer with this sort of long hydrocarbon, they remain completely immiscible to wide range of organic solvent, and it maintain its crystalline properties, right? And give you a quite a smooth interface. This is the FEACM images. I forgot to put the interface of the porous polymeric coating, which is quite rough and porous, okay, which is very obvious. But after you infuse this polymer and go for the molten phase, you get a very smooth interface. And under AFM, you see these fibril things is because of the crystalline domain. Okay? And the roughness is around 20 nanometer, right? Now, If you see under cross-polar microscope, because of this crystalline nature, you see these birefringence all over the places. It says that it's a kind of continuous crystalline network that you have established inside this porous polymeric coating, and because of that, you're getting this property. Not only that, not only just the crude oil and water, you can see various sort of non-polar and polar liquids that you can effectively slide off across these sort of coated interfaces. And they remain quite stable in acidic, alkaline, river water, artificial seawater, and surfactant contaminated water for a few weeks. As you can see here, many of these liquids can be easily slide off. And taking advantage of this phase transition, as you can see, like the room temperature remains solid, but once you heat it up, they become molten, right? So taking advantage of that, even though you incur some sort of physical damage on this interface, you can heal them within a few seconds, right? Because of that, you can see, like if you put the water, it's stuck on that place, but after healing, it slide off. This is a crude oil, okay? It's a very complex chemical, okay, that can also slide off easily after the healing across from top to bottom, right? Now, you can further extend this healing process at least 50 times. It can go definitely more than that. We have just demonstrated till 50 times, and you can coat on a wide range of substrates, okay? And even you can coat a bottle. So this is honey that is basically, you know, like how difficult to dispense the honey from where this bottle, commercial, those bottle. But once you have a coated, you don't even lose a tiny droplet. The same for the crude oil as well. You can coat a entire glass window. You know. So this is just the blue color water, but you see after coating, the just by tilting, you can see, like, you know, you probably got the point, right? So entire such a large object also you can homogeneously coat, right? So it's not that tiny some things you can coat and then say that, you know, you did a miracle, right? So it is quite scalable. Okay. Now, this is the another area and topic which give us the flexibility to learn what is the primary requisite to derive a solid slippery interfaces against selected liquids. When I say like selected liquids, is not only restricted to water. It could be water, it could be ethanol, it could be crude oil, whatever it is. But what are the parameters I should look upon so that I can derive it, right? So this particular design give you the fair idea about it. So instead of this cum-like polymer, we have designed another polymer which is reactive, but the cum-like that component still there. So it's a crystallizable, it undergo phase transitions, and the malic anhydride group makes it chemically reactive. Okay, it's a random polymer. It's not a copolymer. It's a random polymer. Okay, now same thing, you have a substrate, you have a porous network, and then you infuse this polymer there, okay? And depending on this carbon chain length, you can realize a slippery property against various sort of liquids, okay? As I discussed in the last the part. Now, just by changing this mole fraction of the malic anhydride and octadecyl acrylate, you can basically play with this roughness of this coating. Okay, resultant coating roughness you can play with, and you can maintain this crystallinity. Okay. Once you have that, we have a pool of this coating. We try to examine the roughness and surface energy of the resultant coatings. And then we started looking at this contact angle hysteresis. We found that contact angle hysteresis is basically getting enhanced after some point, and that is the trend. If you see, surface free energy as well follows, though this roughness is gradually decreasing. So if the roughness is a crucial factor, then this mole fraction could have been the best should be considered the best for the slippery property. But we found that this mole fraction 0.27 is the best to achieve the least contact angle hysteresis, and it works for both high surface tension liquid as well as low surface tension liquid, that is ethanol and water. Okay. Now, if you go further, we took a interface which is the mole fraction is that 0.27, which is good to slide both water and ethanol, or say more generally, we say that surface tension more than 35 millinewton per meter and surface tension less than 30 millinewton per meter, and then you modify the glucamine. Okay, what about the malic anhydride available only on the surface? Because this is a smooth interface, right? Only on the surface, they undergo this chemical reaction and install this hydrophilic domain and precisely changing the surface free energy. Okay, because of that, what happening? It compromise selectively slippery property against low surface tension liquid, but the high surface tension liquid, that is water or similar sort of, they can easily keep on sliding off. Okay, this is the data you can see. So this is the unmodified one, the reactive slippery interfaces where the water and ethanol both are sliding off, but once you do the glucamine modification, water is sliding off, but ethanol is spilling all over the place. Now, the same interface, if you can further heating it up above its phase transition temperature and cooling it down at room temperature, then it's regain its property back as like earlier. Okay, another thing you please note it, the contact angle of the water initially it was 112, it was hydrophobic, and after glucamine modification it become hydrophilic less than 90, but it doesn't really lose its slippery property. No, anti-weighting property is still maintained there. Okay, but for ethanol it's completely compromised, right? Now, if you see the surface free energy and roughness as is the same interface, right? So the roughness, there is no change whether the chemical modification or you did the phase transition just by melting it and cooling it down. Okay, but what is happening? The surface free energy that is increased to 30 once you chemically modified, and then it dropped down to around 20 again. Okay, and this number is important. If you see the ethanol surface tension is around 22 millinewton per meter, and your interface has to be in that same range, then only the liquid would slide off. If it is above that, then the liquid lose or the surface will lose the slippery property against that particular liquid. Okay, so that was the prime understanding, and now you say like, why the heating does revert back its property? It's because in the crystalline phase you have a limited functional group available in the surface, and that's the point you post modify, and then once you heating it up, it's a molten phase, the polymer segments are basically rearranging or diffusing, and that's the way you see these hydrophilic segments are buried and re-establish this low surface free energy, right? And that has been also further validated through this FTA characterization. So after this post modification, you can see this amide peak is that is appear, and after heating that is basically gone because it's buried. It's not that those bonding are going back. It's just they are buried in that polymer. So the surface abundance is very poor, and rather you can see this malic anhydride component that recover quite well. Okay, so in the surface you have a more malic anhydride group to further modify. Now, after this knowledge, we thought, why not we go for the spatially selective modifications. Once we do that, we can have a pattern that can be apparently visible, or the liquid can recognize it depending on its surface tension. Okay, the same interface, when you expose to the water, it cannot really find that pattern. But when you expose to ethanol, at that's the point it can find it out. So it's a kind of hide and seek, right? So you expose to the water, there are no trace of the water here, but you expose to the ethanol, the red color, there you see this each of these spot can catch that particular liquid, right? Because you have compromised that, selectively compromise the surface free energy there, right? And it's a temporal also, because if you apply heat, you can erase that pattern, and same interface can be reused for multiple time to associate different sort of pattern interface. And as you can see here, this is the schematic and this is actual the data. And then you can apply this sort of principle to sort out the ethanol and water. You can differentiate them. So you have this sort of pattern interface where you put the liquid, whether it's ethanol and water, in the same at a single spot, but the ethanol can find that pattern and can move along that path, but the water cannot find that thing, right? It doesn't matter for water. So it can just follow the gravitational path and go straight. That's the way you can differentiate them. Now, out of this selected pool, any of this you can choose and you can separate it out. Now, you imagine, like, nowadays people are concerned about the waste of chemical and this and that and screening of catalyst and all, right? Now, when you have some sort of chemical reactions, you have to purify them, right? For that, mostly you use this separating funnel, right? And then you extract the product into another phase. Now, suppose I restrict the choice of the reactant and say, like, I minimize the reaction scale to 50 microliter or 100 microliter scale. Can I use the separating funnel? Now, in that case, how I'll separate my product from the reactant? Just to see that whether my catalyst is reacting or not. Sorry? Huh? TLC. TLC you can do, but I'm saying, like, I'm extracting it and then I'll go for the further modification, further characterization like NMR or so, right? So for that, you can have this sort of pattern interface where you can put the oil and water together, or say like water immiscible phases, right? That is what the separating funnel does. And one phase can be catched by this spot, and then another phase can be easily slide off, right? And that's the way, this small scale, you can separate two different sort of liquid from one spot. And many other things can be done. But recently, we're also, as I said, like, have you remember that when we go for the chemical modification, the water contact angle changes, right? From hydrophobic to hydrophilic, though it is not losing its slippery property. That is a very unique thing. It's the same interface depending on its state, right? Whether you go for the chemical modification or a heat treatment, you can play with this contact angle without compromising its slippery property. Now, once you have that, what we recently realized, if you have a hydrophobic slippery property, if you put the water droplet, the contact angle and then contact length, they both, so the contact angle remains same, but the contact length means end to end distance, that is getting reduced and reduced and reduced. That is not the things which you find on a bare glass. Bare glass, if you put the water droplet, it remain in the same place. It's just the contact angle only change. Okay, the contact area or contact length doesn't change. It's just only water contact angle change. But here it's a completely opposite. Here contact angle remains same, but the contact length, that is changing. As a consequence, in these sort of interfaces, you never realize any coffee ring effect. Okay, whereas in a bare glass, you see the coffee ring effect, but in this interface, you won't. I'll show you something at the end. Now, if you have a hydrophilic, these characteristics are very different. This water evaporations, the droplet confinement is very different. initially you see the change in the contact angle, and then you see there are no change in the contact angle, and after that the last phase further again you see some change in the contact angle, and there are some delay, and then this diameter or distance of the contact is changing. So the characteristics are very different. So because of that, you can literally design some sort of very smart pattern interfaces, and that could be useful for anti-counterfeiting applications. Now this is the bare one, as I said. Here you can see the contact length that remain fixed, but the contact angle keep on changing, right? Which is known for all of us. Now this is a three interface like hydrophobic slippery, hydrophilic slippery, and the bare glass. And same volume of the liquid you put, right? And as a consequence, what you see, there is a coffee ring effect, and some part of this has been shown here. Now, in this particular case, can you see like it started with this big area, and it's basically confined to such a small, tiny place, right? Enrichment of the chemical can be possible without coffee ring effect. Now, you see the hydrophilic interfaces, they're the safe deformations. Though it's look like coffee ring effect, it's not the coffee ring effect which you find in a bare glass. They have a certain degree of the enrichment or the contraction, and then you see these sort of deformations because of these computations between the contact angle and change in the contact area as well. Okay, well, so these are basically unpublished data. We're just capitalizing on this. So probably in a few months we'll have a more data and understanding on this particular aspect. So with that, I'll as I got the instruction also, I have to stop somewhere in a 10-15 minute. So I'll stop here. So some of these technologies are in collaboration with some of these industries we are trying to translate, and MRPL already applying some of this technology there. And the ChemGist recently used this, so they are basically doing now trying to pilot scale production of this membrane. You can see here the oil and water is dumped there. It's not oil and water, it's basically aqueous solution of the ethanol and ethyl acetate, and that you can separate out in two separate container, you know, depending on choice of to this membrane. This is the fabric. You can see you cannot really distinguish this coated and uncoated, and there are some of these brand now available in the market where they do, but we can also do the similar things. This is the things probably we did long back, but it just anyway that is there. The slippery paint, something, you know, that is also there. I think this is already displayed. So you can see here the slippery paint, the commercial paint that you can make them slippery. So you don't have to really rub it to you know make the things clean. It's just a spray with a little amount of water. All the dust and dirt will go away, right? And some of this work highlighted in some of these journals. Now, this is the most important part. I'm basically the spokesperson of this lab, and they are the pillar of this all this work. Mostly it's executed by Monideepa, but the others' contributions also they have not really covered most of the things in detail. But yeah, I hope you got some flavor that how simple chemistry can really make a lot of difference when you count for heterogeneous and homogeneous functional liquid wettability. I'll thank my institute and the department, all my collaborators, and Professor Tiprode for giving this opportunity, so that you know we are here today and sharing my whatever my lab doing it in IIT Guwahati and all these funding agencies and industry partners. Thank you so much.
To start with the question, like
Sure.
you have showed so much of liquid wettability and all pattern surfaces. I have a question. What is limiting scalability of that kind of jars that you showed that we can pour just honey and oil?
It's doesn't really limiting. It just that is a standard bottle what I can see in the market. So the emphasis is that even a complex object you can coat. The coating inside of a complex, you can literally appreciate that inside the bottle is a complex geometry, and that is a standard 250 ml bottle, though it's apparently look like a small. So you coat that, and you can show that the product, that the basically food product, viscous product, we know like dispensing that, extracting that is a problem. And then think about there are millions of bottles are with probably 50 ml of honey getting wasted every day, right? But here I think you have seen that I dared to open that movie file again because it might, right? So, so you have seen, even you have not lost a tiny droplet, same honey, right? And I don't know, like, do you have a experience to work with the crude oil? Crude oil is a messy thing. It has everything, and people also don't know what are the other things is there, right? So it's a very complex form of chemical that can also be repelled by these things, And you have seen that window panel, right? The person who are holding with that, do you really think it's tiny? I don't think so. Sorry? Yes, yes. So basically, this is the particular topic where need lot of um, collaborations. You have an interface now. Some other partner has to come, and then they have to need to talk to. What happened? Often we don't talk each other. Okay, and we feel like, oh, come on, right? If I like, what's the big deal, right? That sort of things. But what I realized over this my career is not that old, that long, right? It's just 10 years. 10 years is a very small time frame, right? So in that decade journey, what I found that the small steps can really bring a lot of big implications. But some point, convincing the people is a bit of problem. But you cannot really give up. We all live in a hope that tomorrow will be better, right? Um, so there are tons of reason to get demotivated. That is a natural phenomenon, right? But we have to keep it up and need to try. Everyone's life there are odd, but I feel that someday we'll get some collaborator and we'll execute this. So yes, in any place where you want um, precise delivery of a liquid without losing it, can be possible. Even I know in the bio, the people often do the autoclaving, or say like they spend a lot of money on pipetting tips. This could be one of the simple things, but some point some companies doesn't probably also don't want to make such sort of technology, because then their recurring cost will go away. These are the harsh truth. See, the paint industry, there are many things can be possible, but when I go and discuss about it, they say like, no, we are good. See, that is what many people say, and that is something definitely people should do. But being an academician, being a researcher, being an entrepreneur, is a bit difficult. So right, so there are a different career stage. At this point, I feel that I'm really enjoying teaching. I really learning to teach convincing ways so the people cannot be sleeping mode. I like to see like even the people are there, eye contact, and then I try to make them keep like not sleepy. So that I take it as a challenge, and then see, most of you came with the heavy lunch, definitely sleepy. In our menu is basically rice, right? Still, I think more than 50% will remain alert. I feel like it's a success. Okay. Yeah. Yes, please. Oh, you don't have any questions. Okay. So no question, that means two things. One, that nothing is clear, and everything got clear. Right?
the ones that have different surface tensions.
It's not only different surface tension. What I mean, I'll just let me clear it out. So you mean is only good for those liquid which are immiscible to each other.
Immiscible, yeah, which has like for that the liquid and the solid surface, the surface tensions would be different.
Yes.
If both the liquids have the similar kind of surface tension,
then it will not going to work. Right. So the difference, at least that difference has to be 2.5. If it is less than that, is the problem. Often in the literature, if you see, people take the crude oil or say like different other oil, surface tension is around 30, and they take just a DI water. Surface tension is around 72. Surface tension difference is around 30, 35. But this is a system. It's not only just the oil and water. Even the two organic solvents, they're immiscible. Surface tension difference probably only 2.5. We can successfully separate them.
The precision I'm talking about.
Yes.
What precision we go, like even if for us the difference would not be much, but and we might think that it might not separate, but if the precision could be very high.
Is the precision is very high. That's the way we have decorated that membrane. So what happened, this membrane, it prepares such a way it's compatible with that certain sort of liquid. Even in that, they can identify this difference. 2.5. So that is the limiting. Anything above the 2.5, it works.
It depends on the kind of how we modulate this structure.
Yes. It's basically surface chemistry. Yeah. And compatibility.
Sir, what was the instrument name that you used for the measurement of
force tensiometer? Yeah. So there are only, I think, if I'm not wrong, there might be some other companies also. Mostly data physics, based on Germany. Another is Cruise. Okay, so those are the only two company they manufacture this sort of equipment.
Sir, amazing talk, amazing work. I want to ask that I have understood the overall method that you work with and all the implications it provides. My only thing to ask is that the one you showed where you were pouring that honey from the bottle and all. So if we try to use these methods in something like food technology or just simply making those kinds of bottles or syringes or something like that. So how stable are those films which you make? I mean, while pouring, it might occur that some polymers may stick out into the food that we are eating or the water maybe. So how could you be sure that it will not come out in any way?
This polymer, whatever we have taken, absolutely insoluble in water, and basically we struggle to find a solvent where we can dissolve this polymer. We found only two solvent. That's the place it gets some sort of solubility. Yes. So that's the reason I think that is very less likely. But definitely we need to do in-depth analysis to see like how compatible over the time. But the stability wise, still the some substrate prepare a couple of years back, still it is slippery, remain very stable. Yeah. Yes.
Yes, sir. The chemistry was involved here is a kind of copolymerizations. Like
is a random. No, there are two things. What he's highlighting is just the homopolymer. It's just octadecyl acrylate. The other one, what we did is just for the pattern interfaces and to understand what are the prerequisite to synthesize these sort of interfaces for more fundamental studies. Yeah.